So we want to talk about the rules for integrals that are essentially like the rules for shortcuts for derivatives. So the power rule for integrals, if we think about the power rule for derivatives just for a second, the power rule for derivatives was that if f of x was x to the n, then f prime of x is nx to the n minus 1. So what we were doing with derivatives is we were taking the power down, multiplying it, and then subtracting 1. So to reverse that, the power rule for integrals says add 1 to the power and then divide by that. Okay, so for example, if I have the integral of x cubed dx, and that dx always has to be there, it's just indicating that I'm taking the integral with respect to x. Then, according to the power rule, it would be x to the 3 plus 1 divided by 3 plus 1, and then plus c. And so that gives me x to the 4 over 4 plus c. Okay, that's how the power rule works. And so we could do a number of examples, and we will in a minute, but that's the concept. Now, the only issue is that this does not work when n is minus 1. And the reason it doesn't is because then I would be saying my derivative has a divided by 0 in it, and that's a problem. So we have to consider what happens when x to the minus 1 shows up, all right? And what happens is if you think about ln x, if that's y, then y prime is 1 over x, right? So that means that the integral of 1 over x, because that's really what x to the minus 1 is ln x, because the derivative of ln x is 1 over x. And so if you see 1 over x or x to the minus 1, you know the integral is ln x. If you see any other power, you can use the power rule. So that's the power rule. The next rule is the constant rule, and the constant rule is the exact same as it was for derivatives, because the derivative rule says if you have a constant and then multiplied by a function, the constant just stays, and you take the derivative of the function. It's the same is true for integrals. So in other words, if you had, let's say for example, I had the integral of 4x cubed dx, then what this rule says is that's the same thing as 4 times the integral of x cubed dx, which is 4 times the integral of x cubed. We use the power rule, x to the 4 over 4, and then plus c. And what happens is the 4's cancel. So my answer would be x to the 4 plus c. Okay? Excuse me. So all the constant rule says is have a constant, just stick it out front. Okay? And take the integral of the function. The sum and difference rule, you can imagine, again, with derivatives, the sum and difference rule said if you have a sum or a difference, you just take the derivative of each piece of that sum or difference. And so with integrals, it then becomes the same. So the integral of f of x plus g of x is the integral of f of x plus the integral of g of x dx. And if it's minus, then it's minus. So now we're sort of building, okay, now I can deal with things like this. I can say, what's the integral then of x cubed plus 3x squared? Okay, and I would say, okay, well, the sum rule says you can just integrate x cubed, and you can integrate 3x squared, but the 3 is a constant, so I'm going to write it in front. The integral of x cubed then becomes a power rule for integration, so it's x to the 4 over 4. And then this 3 stays, and the integral of x squared is x cubed over 3, and then we just put 1 plus c. We don't have to put 2. Like, we don't have to put plus c here and plus c here. Because if you add two constants together, you just get another constant. And then what happens here is these 3's cancel. So my final answer is x to the 4 over 4 plus x cubed plus c. Okay? So that actually incorporates the sum and difference rule, the constant rule, and the power rule. All right? And so let's imagine that I gave you something like this. I said, what's the integral of x to the 8 dx? And you would say, well, that's just a power rule, so I add 1 to the power and divide by it, and I get x to the 9 over 9 plus c. All right, if I gave you something like this, 4x to the 5 plus 16x cubed, again, we're going to apply, first of all, the sum rule and the constant multiple rule. And so we end up with the constant stays, and I take the integral of x to the 5, which is x to the 6 plus c, or x to the 6 over 6 plus c. But again, we just tack the plus c on at the very end. And then the 16 stays, and the derivative antiderivative or integral, sorry, my mind's, it's hard to go back and forth, and you'll notice that sometimes, but the integral of x cubed is x to the 4 over 4, and then we just simplify. And that's our answer, okay? Now, you can also think through, what about other integrals that we know? And here's what we're going to do. We're going to think about these based on the derivatives that we know, okay? We're just going to rewrite them. So we know the derivative of ln x is 1 over x. That means the integral of 1 over x is ln x. We know the derivative of e to the x is e to the x, which means the integral of e to the x is e to the x. They don't change, okay? And these all have plus c on them. We know the derivative of cosine is minus sine, so that means the integral of sine is minus cosine, okay? And we can go through them all like that. So the integral of cosine is sine of x. The integral of secant squared x is tangent x plus c. The integral of secant x tangent x is secant x plus c. And you know all of these because you know the derivative. So the derivative of tan x is secant squared, which means the integral of secant squared is tangent x. So you just have to think backwards, all right? The integral of cosecant squared is negative cotangent x because the derivative of cotangent x is negative cosecant squared. So we put a negative there and it makes it positive. And the integral of cosecant x cotangent x is negative cosecant x plus c. All right? So in other words, we're just using, all we're doing is using our knowledge of derivatives backwards. We're saying if we can write that the derivative of cosecant is negative cosecant cotangent, then we can rewrite that as an integral instead, that the integral of cosecant cotangent is negative cosecant. All right, so that leads us to be able to do other questions. Here's a question that's a product, and just for now, we don't have a product rule, so we expand first. So we expand this, and we get this. Okay, and once we've expanded, then we say, no problem, we can integrate that. So the integral of 2 is 2x. The integral of x is x squared over 2. The integral of 2x squared is x cubed over 3 times 2, so 2x cubed over 3. The integral of x cubed is x to the 4 over 4, and then we tack on a plus c. All right? It's important that you know these integrals, but you already do because you know the derivatives. So if we go to put something in there like these, okay, you should be able to recognize then, all right, I've got 1 over t. You've got a 2 there, so the 1/2 is just going to stay. The integral of 1 over t is ln t. Root 2 is a constant, it stays there, and the integral of e to the t, the integral of e to anything is e to anything, and then you go plus c. All right? So we're going to practice more of these as we go through this, but it's a general idea. If you look at something like this, here's another example. We say, okay, well, this one's a trig one. I can't integrate a product, so I'm going to multiply first secant x tangent x, and then I get secant times cosine. Secant x tangent x can't reduce, really, but secant x times cosine x can, so I'm going to make it 1. And then I'm going to integrate secant x tangent x. You should recognize that as secant x, because the derivative of secant x is secant tangent, and then the integral of 1 is x plus c. Okay? And then here's another example. Secant squared t minus sine t. So if you integrate that, you get tangent t plus cosine t plus c. All right. And here's another list of derivatives. There's only a couple on here we didn't mention. We didn't mention this one, and we should have. So b to the x, it's b to the x divided by ln b. But these are all your integrals, and we already listed them all again. But it's another helpful tool to have them all listed there. And what we're going to do is we're just going to practice taking the indefinite integral first. And then what we'll talk about is, okay, now that we know how to do that, what about the definite integral? How do I deal with that? And that will be our next video on the fundamental theorem of calculus. And I mean fun.